I'm on day 2.
Hi, Violet.
Hey, Bob.
Yo, Mr. Sarah Watt.
Don't hold my spot. Okay? So now I'm on day 2 of separation of variables. Okay? So I want to talk a little bit. I want to start to get into the different types of differential equations we have. Okay? We did the simpler ones yesterday. We're going to look at some that are slightly more complicated today. Exponentials and, more importantly, logistic. Don't talk to her. Don't listen to him. Okay? Okay? So, what we're about to talk about is going to be used for exponential growth and decay problems. Okay? Now, nothing, if you guys remember anything from the video yesterday, nothing in nature occurs with exponential growth or decay. They all turn into logistic curves because they have these limiting factors, except for a couple things, like stuff that's radioactive. Okay?
Radioactive decay.
Radioactive decay, that's going to decay, and it's going to decay, and it's going to decay, and there's nothing going to change that. Okay? So we do want to study these. Okay, but this is still modeling. Okay, I think that Swabata is wrong. You guys still?
She was reading
It is spelled with an A.
That doesn't mean that the second one is better.
Oh, shoot. We suck.
It's okay, there's no shame.
Critics, man.
They don't teach you for your English.
Okay. So, in exponential growth or exponential decay, we assume the rate of increase or the rate of decrease, if it's decay or growth, of a population at any time is directly proportional to the population. And our way of doing that is by writing this differential equation, that the derivative is some factor times the population. It's directly proportional. Okay? So we keep that in mind. So if it's exponential growth, it'll look like this, where k is positive. Does that make sense? Okay? And let's talk population. And the initial population is going to be this value y sub 0, whatever that is.
Mr. Taylor, do you have another sheet? I forgot my packet.
No, but you can write things
I
down.
was studying for this quiz.
It's all being recorded. Okay. If it's decay, we still like to keep the k, the number k positive, but we just end up negating it. What's that? Okay. All right, thanks. Okay. So we'll just have a negative. Think of it as a negative growth rate instead of a decay rate. Okay? Can we handle that? All right. So even though the growth rate is dy dt, we commonly refer to k as the growth rate. Okay? Even though that's misleading. Yeah. All right? Okay. All right. So you guys have a little bit of space there, right, underneath that, right? So I just want to move this over a little bit. Okay. So if we do what we did yesterday, what would we do yesterday if we had something like this? Thank you very little. So if we separated the variables, we would have dy over y equals k dt. That would be our first step. Our second step would be to integrate both sides. What's the integral of 1 over y dy? ln y, well, we're talking about population, and we're going to assume it's a positive number, so we're going to let, these are real world problems, so we're going to let that, ignore the fact that you're right, okay? And then over on the other side, we're going to get
KT plus C.
kt plus c. You just got to move this down a little bit.
There are no numbers again.
That's right. Okay. So when time is 0, when t is 0, okay, we already said by default we'll have y 0. So y will equal y sub 0. Okay. So if we just plug that stuff in here, that means that it'll be at time equals 0, y will be y sub 0. So ln y will equal
Y0. Y sub 0.
Y sub 0 is equal to C. So ln Y sub 0 is C.
hold on. I just kind of did that out of order.
These are blue. Color code change from angles.
It's not working.
He said that we're on audio.
And the shading around
What code is this?
Oh.
Okay, I'm sorry. I'm back. I skipped something.
What color?
So we put in our initial condition, and then we get ln y will equal, wait, it's not ln y sub 0, right? Will equal C. Everybody see that? Put in our initial condition, working with that, and I put that back into my equation now. That means I have a working equation that looks like this, that the ln of y will equal kt plus the natural log of y sub 0. All right? Now, currently, that is in logarithmic form. Let's put that into exponential form. Okay? So let's convert it from logarithmic form to exponential form. So remember, this is natural log really means, hello ladies over there, natural log really means log base e. Okay? So if I want to convert this into exponential form, that means e is my base. So it means I'm going to write it over here. E to the, all of that, e to the kt plus natural log y sub 0, that will equal y. That's just converting.
What is that type of form called?
That's just, this is logarithmic form, this is exponential form.
Wait, can you just do e to the kt
That's what we're going to do.
plus y sub
That's exactly, yes. Yes to everything you guys are saying, okay? Yes to everything you're saying. Okay? Now, when you are adding exponents, it's the same thing as if you were multiplying like bases. So that's y equals e to the kt times e to the ln y sub 0. Thank you.
Oh my gosh,
Okay? Now what is e raised to the natural log of something?
whatever the something is.
That's something, whatever the something is. So y equals
E to the kt.
y sub 0
E to the KT.
e to the kt.
That was really good. That was great.
Okay? And that is
Exponential.
what we use, right? That's what we've been using. So when we have this, I'm just going to bring this down now.
Y sub 0 e to the k.
So I've got let's use population as an example. The population at any particular time is the initial population times e raised to the growth rate times time. And or if it happens to be decay, y equals y sub 0 e to the negative kt. This would be for decay, and this is going to be for growth. Okay? So this is my growth formula, my exponential. Sorry, this is my exponential growth formula. Here's my exponential decay formula.
Oh. Wait, I have a question.
Yes.
How did you go from e ln y0 to y0?
What is e raised to the natural log of anything? It's the anything. Because these are inverse operations, so they would cancel each other out.
Natural.
Just go with it.
Alright.
You don't need to do this derivation. All you need to do is remember this. Okay. So that's for any kind of exponential growth or decay. So we'll look at a simple example. The world population in 2011 was 6.9 billion. growing at a rate of 1.1% per year, assuming an exponential growth model, estimate the world population at the beginning of 2030. So what is y sub 0?
That's too expensive.
6.9 with a capital B. Capital B for billion is fine. Okay? What is K, our growth rate?
So, what is it? 1.0, wait, 1.0.
This is it as a percent. We're always going to write
0.011.
we're going to write K always as a decimal. So it's going to be 0.011. Okay? And the time in this particular problem,
We've been doing this since like
19 years. Okay? Yeah, we're not really doing any calculus yet. So y of t, according to the formula, well, y sub 0 e to the kt. So y of 19 will equal 6.9 e to the 0.011 times 19. And that's approximately 8.5 billion. Okay?
That's a lot of people.
Assuming exponential growth. Okay? That's assuming no COVID-19. Right?
and that's assuming
All right. So, no calculus involved yet, but we did use calculus to. No, we actually haven't. Well, it's a differential equation. I guess you could say we did. Okay. So, doubling time and half-life. Doubling time and half-life. We've got this formula: y equals y sub 0 e to the kt. Okay. So, the time required to double, or the time required for the original amount of something to reduce in half, which is half-life, right? These are all measures of time. Depend only on the growth or decay rate, not on the original sample size. Okay? If I have 100 grams of plutonium, okay, it'll take the same amount of time to decay to 50 grams as if I had 1 gram of plutonium decaying to a half. Right? Same amount of time. Yes, ma'am.
Isn't there something like the rule of 72?
The rule of 72 is definitely this is how the rule of 72 came about. Yes, ma'am. Okay. The rule of 72 says if you want to know how long it takes an investment to double. Okay, so if I had $10,000 and I put it into an account that or put in an investment that was 5% a year, okay, how long would it take to double? The rule of 72 says take 72 and divide it by that interest rate as a percent. 72 divided by 5 is 14. It would take 14 years to double. That's related to natural. Karen. It is a natural log application. Okay. All right. So if I want something to double, then I could let the initial, and if the initial amount is independent, I could let the initial amount be 1, and I could let the final amount be 2, because it's independent of the initial amount. And that would be e to the kt. Okay? How am I going to solve this? I don't need the 1 in there anymore. I'm going to get rid of the 1. You can natural log both sides. If I natural log both sides, that's the great and only way I know of getting the exponent out of getting the numbers out of the exponent and down below. Okay, so what's the natural log of e to the kt? So kt will equal natural log 2. So I could either solve this for k or I could solve it for t. No, I mean you'll want to do both. If I solve it for t, what's it for t? ln2 over k. If I want to solve it for k, it's ln2 over t. Okay? This right here, that's the doubling time. Okay? time it takes to double.
What's this other thing?
The growth
Halving
rate.
time.
The growth rate.
Can you go over how you got KT from the other one? Just
The
a refresher.
same way we did the last question you asked.
No, it was different.
No, it isn't. It's the same. Remember we had e raised to the natural log of something?
Yeah.
Here we have the natural log of e raised to something. They're inverse operations. They cancel each other out. Also remember when you take the natural log of something, you can just drop that and bring that down in front of the logarithm. Remember that?
Yeah.
And what's ln e?
One.
Booyah. Okay? All right. Christians out there? Any Christians out there? No. Not yet. How long will it take the world population to double? I don't have this question on here. It's on yours? Okay. How long will it take the world population to double?
Or 732.
LN2 over K.
732. Period.
Time will equal ln2 over k. What's k for us? 0.011. What's ln2 divided by 0.011? I don't know. I didn't do that. Calculator. Who's got one? Somebody.
I just need mine.
You're too late.
What does this have to do with Christian?
Where's Ellen? Where's Ellen?
It's right there.
Oh my god. He's
63 years.
63.
Okay?
63.
63 years. All right.
Wait, go back.
No, I'm
wait,
not.
go back. What do you mean?
I
was
refuse.
working it out with my calculator.
I refuse. Okay? I refuse.
What does this have to do with?
Wait, this is the same.
All right. Carbon 14. Carbon 14 has a half-life of 5730 years. Okay? If 100 grams of carbon 14 are stored in a cave for 1,000 years, how many grams will be left? Let's see. We've got y equals y sub 0 e to the kt, e to the negative kt because it's decaying. Thank you. So what do I plug in here?
You put 100 for y sub 0.
100 grams.
And then you
E to the what?
Yeah.
Negative
K.
oh, is it?
So 573.
Oh, 573
5730.
times.
That's not the thing.
That's not.
Oh wait,
That's the
that's
time.
the
Come
I know.
on now.
KT.
You need to solve for k.
Carbon has that. What
That's
is
over
is
K.
K?
Oh, I guess
What
so.
is K?
K.
0.5.
K is what?
0.5.
But what is it?
ln2 over t.
What? What is K?
ln2 over 5730.
Hold on.
No, it's 1,000.
Yo, oh, that's a small number.
Wait,
What is
oh,
K? Can somebody tell me what K is?
Oh, wait, no, it's 5730.
No, it's not.
What is K?
I got 1 point, oh yeah, 1.20, 1.21 times 10 to the negative.
Jesus.
Times 10 to the negative 1.
4. So 0.000121.
0.00.
3 O's, 1 to 1.
Wait, where
I know the science.
Wow. Nice.
Wait, why isn't it
You know
1,015?
It's
0.000121. Right, that's K. Okay? So that means my formula for carbon 14. Sorry. So my formula for carbon my formula for carbon 14 is y sub 0 equals e to the
100.
negative 0.000121 t. That's what it is.
It's 1,000. Can we fill in more?
That's my formula for carbon 14. I can plug different things in. Like in this problem, I could put 100 grams in here and then get my answer. Okay, no, I could put 100 grams
Didn't we
here
do it?
Wait, I'm confused. Why are we using 5730 though?
and 1,000 in here, and I get how much is left.
Yeah, like,
Okay, so
but isn't t the same? That's
this
Oh
is
wait,
the
yeah, I'm kind of
this is the general formula that I'm going to use in both example 6 and in example 7. That's the whole point. I'm going to use this twice.
Wait, what is that?
So in number 6, I'd say y equals 1,000 to the negative 0.0000121.
Bro, what are you?
That's what I said. Times 1,000, right?
Oh. I mean,
Someone else can do that.
so where's the 5730? Oh, we use it.
I got it.
How many grams?
How do you think that I pass this?
88.6.
That makes sense because in 5,000 years, half of it would be gone. I only did it for 1,000 years, so it should be less than half of it. How many years? How many grams?
How is
88.6.
1,000 is one problem?
Okay. Now, Shroud of Turin. Any bibliophles out there?
What?
Okay. So the Shroud of Turin, somewhere in Turin, Italy, they have this shroud there that it's like a shroud. It's dead bodies get wrapped in these things, and the shroud actually looks like this. Okay, so somebody said, "Hey, I think it's the shroud that Jesus was wrapped up in."
How would they know?
Well, that's how these things get started. The claim was this was the shroud that Jesus was wrapped in when he was put in the tomb after you Jews out there killed my
So I
Savior.
don't know.
No, yes, of course.
You know what I'm talking about.
Pilot can hear you.
Don't do this Pontius Pilate stuff on me and blame it on the Romans, okay? We all know. Crucify him. Okay. So this is a sacred religious thing. So what some scientists said is, hey, let's carbon date this sucker and see how old the shroud is.
It's not Jesus, is it?
Well, let's find out. So in 1988, the Shroud of Turin, so the shroud that Jesus of Nazareth was supposedly wrapped in, was examined and found to contain between 92 and 93% of its original carbon-14. So we're going to use this information to date the shroud.
How do you know it's of the original?
Because living things
Oh.
have a certain percentage of carbon-14 in them. Living organic hydrocarbon things have a certain percentage of carbon-14 in them, and as soon as they stop living, that carbon-14 stops being produced, and the amount in that substance starts to decay. Does that make sense?
Yes.
That's how that's carbon dating. That's how carbon dating works. Okay? It doesn't mean you can go out and ask carbon if they want to go see a movie. That's a different thing.
Okay, cool science.
All right. All right, so let's do this. So what's y going to be here? Y equals y sub 0 e to the negative 0.000121 t. Okay. So what are we going to plug in?
190.
What?
Just plug in 1.
Yeah, plug in 1.
Or just 100.
Yeah,
1 and 0.92.
1 and
Or you
0.92.
already played 2,000 years. It's fine.
So 1 and 0.90, let's say 0.92.
That's
We'll
also
plug those in. Okay. And then it's e to the negative 0.000121 t.
But could you also do 1988 for time or for years?
Hold on.
Yeah, that's.
Hold on.
Oh,
Hold on.
Oh, yeah, you're
Oh,
right.
let's just try it. So we're going to take the natural log of both sides. So the natural log of 0.92 should equal negative 0.000121 t. T will be that divided by that. So what is the natural log of 0.92 divided by negative 0.000121? I'm getting something around 600.
689.
689? What? 689.
I don't think it's Jesus.
So how do we put this in context?
That was
First it died.
Subtracted from?
today.
No, not today.
1299.
From the day it was the test was done.
He died.
So 1988 minus 689. That means it's It's around the year 1300 AD.
That's after his death. How did he die after his death?
I'm sorry. BCE 8. What do you guys say if it's not BC? CE? CE. CE.
Isn't it like mean?
What does Anno Domini mean anyway? The year of our Lord. Okay, CE. So, what's the conclusion?
Jesus died
Is Jesus.
It's a shroud. How old's the shroud? What year was the shroud created? 1300. So this was some middle ages dude, or dudette with a beard.
Like, I'm looking at that.
It's the person's like this.
I see it.
Yeah.
Okay, I see a person like that.
I want to be shrouded.
Yeah.
Hands crossed. Hands crossed.
No, but the dead
What?
things can be losing.
Who knows? I mean, because Rome was in Italy, and actually it still is. I think Rome is still in Italy.
Rome is a city.
Well, I mean, it's where the religious artifacts would have
You know,
gravitated
Italy's
to.
on lockdown.
In the whole Roman. But yeah, but who knows? You know, how these things start. You know, it's like people say, "Oh, this is a part of the crucifix." You know, it's like, how do you know that's a part of the crucifix? Okay. All right. Okay. So, no calculus involved yet. That's just algebra 2, right? All right. So now we're going to talk about a logistic model. Okay? Which is what the intro with the video yesterday. Okay? So, in general, populations grow within an ecosystem that can only support a certain amount of individuals. Okay? We call this number the carrying capacity, right? Ecosystems can only carry a certain amount of whatevers, okay? And we use the letter L. Guys aren't listening. We're going to use the letter L to denote the carrying capacity, or the limit, so the population limit. Okay? So when the population exceeds the carrying capacity, what happens? Then the population is going to decrease back towards the carrying capacity. Okay? When the population is less than the carrying capacity, it's going to be increasing. So we can think of in terms of what's happening with the derivative. If the population is currently over the carrying capacity, okay, if the population is greater than the carrying capacity, then the slope of the tangent at that point will turn to be a negative number, because it has to decrease. So when the population's less than the carrying capacity, it's still on the growth curve of it, so that the derivative will be positive. Okay? So we can tell where we are on the curve by the derivative, or where we are on the derivative will tell us something, or where we are on the curve will tell us something about the derivative. Now, when the population's in balance, we reach that point where it's leveled out, slope of the tangent, 0. Okay? When the population is really, really, really far below the carrying capacity, that's that part of the curve. You guys remember the carrying capacity curve kind of looks like this? Okay? When it's really, really far below the curve, what is it experiencing here? Exponential growth, which we just went over. Okay? Exponential growth. As it gets closer to the carrying capacity, it goes from exponential to logarithmic. Okay? So when the population is, it goes logarithmic. Okay, so, all right. Now, the point at which that changes, whoops, sorry. This is L, my carrying capacity, and I do that really crappy. Sorry, it should be more like here. Okay? This point is always half the carrying capacity. Always. Always. Okay? And the slope is 1. The inflection point. When it goes from exponential to logarithmic, that point is called the inflection point. It's always half the carrying capacity. Okay? Now, a differential equation that meets all of these criteria that I just listed. This is the formula for it, okay? You saw that yesterday in the video. Here's K, our growth factor, okay? And then here's another factor that's meant to tamp down that growth factor as you get closer to the carrying capacity, right? So this is going to be a number that's smaller than 1. That makes sense because it's 1 minus this. But it's also smaller than 1 because it's going to slow down the rate of growth. Okay? So here's my differential equation that's of import. What is L? L is the carrying capacity. So we can identify that right away. And notice that Y gets plugged in here twice, and I talked in the video about that because the rate of change is a factor of how many people are already in the system. So it's a factor of that. Okay. All right. So that's called the logistic model. Okay? Yes, it is an AP question. This is from the 2004 free response question number 5. Hold on just a second, I want to make sure I get through this. Okay? So, a population is modeled by this function. This looks exactly like what we just had, right? And I could look at this right now and tell some things right away immediately. Hey, Priyanka, immediately. Like, what's the carrying capacity? 12. 12. Right? Right there. That's the carrying capacity. Where, not when, but what will be the point where the point of inflection occurs? 6 along the y-axis. Okay? So so the carrying capacity is 12. So question A, if the population at time 0 is 3, okay, what is the limit as time goes to infinity? In other words, where's this thing going to head out to? Does it matter that there's a 3 there? What if it were 14? It's still 12. What if we're 100? It's still 12. Why is it 12? Because 12 is the carrying capacity. It's the long-term equilibrium value of the population. Okay? If the population is 20, what's the limit? It's 12. Okay? It's carrying capacity. All right. Now, let's do part B. Okay. If the population is 3, for what value of the population will the population be growing the fastest? For what value of the population is the population growing the fastest? Thank you. 6. Why 6? It's half the carrying capacity. The point of, right? Half the carrying capacity, okay? 6. Half the carrying capacity. See, so you can answer some of these questions just knowing what we talked about. What the L is, what that means, half the carrying capacity. Okay, now, so no calculus yet. Now we got to do the calculus part. All right?
I thought the slope would be 1 at 6. Isn't it like exponential?
Yes, the slope is 1 at 6.
But then,
That's where it's
but before that, it's
growing the fastest.
It's not growing the fastest.
Yes, it is. That's the point of maximum slope.
The steepest part of
Because down here the slope is going to be less than 1, less than 1, less than 1, 1, then less than 1, less than 1, less than 1. You got it now? Usually? Okay. All right. The slope will be, well, that's what they said, the slope will be 1 right there. Okay, now let's get to the calculus part of it. A different population is modeled by y, where we've got this going on, and it's a separable differential equation. Okay, so we need to find the general solution given the initial condition. So let's do C. Okay? So what do we got to do?
Separate the variables.
Thank you. If you separate the variables, what do you get? dy over y equals
5
doesn't equal 5.
No, I know.
5 dt.
Doesn't equal 5. 1/5.
Oh yeah.
1/5. 1 minus t over 12 dt. Hmm?
You can integrate both sides.
Sorry. Now, you could distribute the 1/5.
No, you don't have to.
Why wouldn't you distribute?
You can distribute the 1/5.
You can just, when you integrate it,
Why
you can
not?
take it out.
You can just wait. Why don't you just put it on the other side?
I don't care,
Do it eventually.
but I don't care. That's what I would do. I would multiply. I would distribute the 1/5. Why not?
You can just do it after.
Well, you could have done it before.
You
Yeah, that's like what he's saying.
I guess.
What? Why would I do that?
Why would you do it before?
Why would I do that?
But why would you do it before?
Why would I do that?
Integrating is hard if the number's big.
No. 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 If it's in this format, what does it tell me? Tells me the carrying capacity. If it's in that format.
But if that's not, it's not in that format anymore. You distribute it.
Yeah, but it's not enough fun.
Because now it's 1/5, not 1.
It was already in there. Kind of messed up.
Exactly. So why don't you integrate that 1/5? No, but it does now.
Oh yeah, you're right.
No.
No, you're
No.
right.
Yes.
Oh, yes, you're right.
No, what is
Hi, Violet.
on the outside? That's it.
No, it does not matter.
All right. So it
Wait,
doesn't.
why are you doing it like that?
Yes, because it
Wait,
does
why don't we-
So what did you look like?
Yes,
All right.
Ariel.
So I'm getting it the way now.
Integrate. Integrate.
What's that mean?
What's the integral of this?
Progressive.
Yeah, but
I heard L in absolute value of y. Thank you. Yeah, I know. All right. I know. We know it's going to be positive. So we've got what here? T over 5 minus t squared over 120 plus c. Okay? Alright? So we need to find, we have an initial condition, right? Just slipped off there. 0, 3. So y will equal, getting this into exponential form, y will equal e to all of that. Okay. Now, if you're adding c, it's the same thing as e to the c, and e to the c by itself is a constant anyway, right? E to the constant is a constant. You got that? So I could just say this simply: y equals some constant e to the t over 5 minus t squared over 120. Because e to the c is a constant. That's k. K equals e to the c.
Is it K though, like
I think you did
Fine.
that in the homework.
Fine.
Yeah.
I didn't get it.
Plug the zero. Plug t
Yeah,
in.
like e to the c.
Plug t in for 0, and what do you get? Y equals what? And what's k? What is y though? So 3 equals k. Okay. So if 3 equals k, 3 equals e to the c. Right? Right. Well, I mean, you could simply say now, hey, I've got a formula that y of t is 3 e to the t over 5 t squared over 120, and then you could just there. Yeah. There's my formula. Then you'd have to get the part D. Okay. That's what you guys have.
Oh, I just, is this really left down?
Morning stretch. Wait, no.